Well, who don't love diamonds, especially women's? I guess everyone. So, what are the diamonds? These pretty things which shine all the time, probably, and we love wearing in ears and hands, and we love them to ask for our husbands and boyfriends to gift us, as usual. Okay, but these pretty things comes little bit of history I wanted to tell you because the most expensive diamond in the world sits in the crown of Queen Elizabeth. She's dead already, but the diamond sits there. And that diamond is originated from India. It was from the 5,000 years ago. It was with us until 19 or 1853, and we're still struggling to get it back. Okay, part of the story. The diamonds can be colorful, but when they are colorful, they have some defects, which means they are not pure. You, being a normal person, we might don't know that the colorful diamonds have some defects. And nobody wants a defects clothes, furniture or something. But we physicists love them. Why? Because in the quantum worlds, diamonds look like this. So you shine some lights, you encrypted some information over it, collect it, and pass it out. So we love defects. Okay. So why and how we can use these diamonds in the quantum world? It's a big question because right over, from 10 years before, everyone is jumping in this field, and it makes people so furious that everyone wants to do quantum physics all over the world. But why? So today I'm going to explain you a little bit very basic how it works and what is useful. So the diamonds on the prospectus of physicists look like this. It have a spins, electron spins, and it have a nuclear spins. So these spins work when you give a driving field. And the atomic structure is shown like this. It's basically it's a lattice. It comprises of a carbons atom attached together with different angles, and then you have a carbon. Okay. So why we are using diamonds, especially to make a quantum world or a quantum application? Because diamonds are rich in a point defects. As I mentioned before, defects are more important for us. So these defects give us a freedom to work and change the optical and electrical properties of the host material, meaning you can put some other different material inside the diamond, which is the host. Sorry, the host is a diamond. So it can emphasize and change a lot of properties. Another is the very prominent color center in the diamonds is nitrogen vacancies. And they usually grown at high temperature and high pressure. These type of diamonds, if you are lucky enough, you can dig it in the nature and you will be very lucky, but it's once in a million. But we can grow these diamonds in the lab artificially. Okay, so I have a question for Rihanna that shine like a diamond. Wow, pretty cool. But diamond really shine? Can anyone answer? Okay. They reflect. So she should contact us. Okay. So when you have the defects, they process a quantum properties. What are these properties? Today I'm not going to explain you a whole bunch of quantum physics, just main three properties and the promising applications. Okay, so I mentioned when you have nitrogen and vacancies, then the diamond color can be pink. And if you have different impurity or a defects, you can have blue diamonds, you can have green diamonds, and so on. So that's the lattice of carbon atom. So the black dot arrows here compresses with the carbon atom. So this is just the diamond, pure diamond, as you call. And so this is the vacancy, what I am explaining. So the N is a nitrogen, which is a removed carbon atom. And you have a one missing atom, which we call vacancy. So when you have this arrangement of the vacancy inside the carbon atom, then you have a diamond with defects. Okay, So the diamonds in the lab actually look like this. So what happened really here, you need to keep this in mind, one single sentence, which is the base of this talk, is that when you shine a green light through the diamonds, they absorbed it and they re-emit as in red. So this you need to keep in mind during the 15 minutes. Okay, so what are the properties? Let's explain one by one. So this arrangement, as I mentioned before, is the nitrogen vacancies. So when you shine a light, as I said, when you shine a light, they absorb something and they re-emit. What is meaning re-emitting? Re-emitting means it's re-emitting in terms of the light. And we all know that light is nothing but a photon, which is a quantized quantity, light and a matter. So they emit one photon at a time. And trust me, you can count them one over one. Okay? Cool. What happened? The another property is a spin. So spinning means you stand at one particular point and spinning around. So the photons, how they are quantized in this atomic array. So you have a spin. This N and V centers is working as a single quantity. So the red arrow here represents as a spin down. You need to keep this in mind that this spin is only related to the NVs only, not with the other carbon atoms. It can be up and it can be down. This is the another property of the NV center, which is a spin, and it is a quantum mechanical property which is related to the angular momentum. So, and this spin is also work as a magnet. We love magnets since we are a child, so the magnets is made up of several electrons which have a spin, and it can be up, down, up direction as I shown here. So what happened in the NV center, when you have a spin or a magnet which behave like a spin, and in the north pole, and you emit the light, the photon emission in a one direction will come faster. More faster, more faster. So this is the property that you can control. The more photons you want, you need to keep this magnetic spin in a one particular direction. And if you revert the direction of the magnetic spin, the photon emission will be a slower emission. In other words, what I am trying to explain you, that this is the main property of the NV centers in the diamond that you can control by applying a magnetic field. I don't need to care about what is the spin of this electron or the photon. I should only know that in which direction the magnetic field is applied. Okay. So there are type of NV centers, as I told you, that you can implement these defects in the laboratories. So you can know whether it's a negatively charged center or it's a neutral or it's a positive. So what makes them curious? So now the NV center for us is working as an individual identity. We know that we have the NV center, which is a defect, and it works as a needle of the compass. So the needle of the compass can be up or the down, depending on the magnetic direction. So you need to forget about the spin here, which I put already before, sorry for that. For example, if you have a magnetic needles which both pointing up direction, and you have a needle which point down, and you have a needle which is up and which is down. So once I know this, that where I put my magnetic field, I can tell you that the electron or the photon is having which type of spin. So, meaning, you just need to put the magnetic field and don't worry about the spin, because the more photon will come, I can tell you that this is a spin up or a spin down, or there is no spin at all. Okay. It's the same. You shine the green light, a bit more visual, and you have a red, as I told you. You are collecting emission of the red light, and you have a less red light. Again, you have this spin, You shine with a green laser, and you have a more red. That means the more red gives you a 0 spin states, and the red light gives you +1 states. And how do you observe them? So in our lab, we absorb them by fluorescence microscopy. And how do we flick this NV center spins? We apply a microwave frequency, and then I can flip this spin states. And there are many more applications by using this idea in terms of absorption more and more photons. So this is in the lab. Okay. So here is the big picture of the diamonds with the different type of lasers you are shining and why you are doing this, what's the purpose. So basically the concept for me to use this theory or this experimental techniques is to make a memory device that you can read something and read out. In order to do that, we use a different wavelength lasers, meaning here you have a square wavelength which is 532 nanometer. Okay, something is wrong here. Never mind. So you have 532 nanometers wavelength, which is like a square one. That's one. So if you're, what does it mean square laser? That means it's in terms of the pulse. It's a bit of a technical terms. In the physics, we use signal generators. You have a different type of waves, square wave, pulse wave, and something. So this is what it is. So you have a square wave here, and when you shine with that, by doing this, what you can do, you can read out of the NV center electron spin, and then mixing charge states. On the other hand, if you have a chopped one, what you are trying to do is, you're trying to do a better polarization stability of these spin states and the charge states. And the many more, that depends on your requirements. You can play around with these NV centers and use in the applications. So what are we doing? It's a bit simple. Our goal is to spin pump these states by applying a resonant excitation. This resonant excitation is depend on the wavelength. And the other goal what we are trying to achieve is stabilizing this charge state by off resonant excitation. So the research question is, what wavelengths and power are required to optimize this charge stabilization? So we have two candidates from the literature. It's a red wavelength, a red laser, and 1017, which give us sharp absorption resonance. And how do we do that? So we have two methods. We do sequential two colors excitation, one by one, and then polarization pulse excitation. Okay, so this is my scientific work. These are the diamond in the lab actually look like. This is a small, tiny, 2 by 2 millimeter. It's surrounded by a tiny magnetic field. Then you have external magnetic field applied. It's about like millitesla something. And that's the microscopy. I built it. You have a different source of the wavelength of lasers. It's going inside, and then you have a sample. So this sample basically is cooled down by a cryostat. So you need a temperature of like around 6 Kelvin to work over these samples. They don't work at room temperature. Different modules through controls and everything. And that's it. And then we control the polarization by the spin states and combine both states together. So conclusion is that we believe that these centers will implement in the future of quantum networks. And what are the networks? So you can build a memory devices here. You can read, input the signal, write, and then somebody else can read it out. Then you can have the repeaters, actually people working over it in the one lab to one city to another, and then you can make a quantum networks. Okay, and that's my group of Fürstenberg, and I work with Elion mostly and of. Thank you.